días a todos y a todas, y a quien esté siguiéndolo de alguna forma en streaming. Bueno, este es un placer para mí tener que estar aquí en este lugar, donde debería estar el decano de la facultad, pero por razones médicas pues todavía no está operativo. Bueno, vamos a presentar la primera conferencia, el primer workshop en física matemática y geometría algebraica sobre integrabilidad, geometría y teoría cuántica de campos. En este caso me acompañan en la mesa pues, el profesor Pierre-Julio Tempesta, que es el organizador del ICEMAT en comparación con la UCM, y el conferenciante Motohico Mulase, ¿okay?, que nos va a dar una conferencia muy interesante sobre secuencias enteras milagrosas. La verdad es que el campo de las secuencias enteras es una cosa que cuando uno se pone a navegar por él es como si estuviera haciendo turismo matemático, disfruta con algunas de ellas, hay un montón de curiosidades y de utilidades científicas, y es un placer pues, trabajar en ese tipo de problemas. Entonces, sin más preámbulo por mi parte, le paso la palabra al profesor Pierre-Julio Tempesta para que os haga una presentación del conferenciante desde el punto de vista científico. Muchas gracias.
Muchas gracias. So I will talk in English now. So good morning, everybody. It's a great pleasure to have with us today Professor Motohico Mulase from the University of California, Davis, which is the speaker of this new colloquium, which inaugurates the for this academic year, the series of the joint mathematics colloquia, which are organized by the Universidad Complutense de Madrid, together with the ICEMAT, the Instituto de Ciencias Matemáticas, the Universidad Autónoma de Madrid, and the Universidad Carlos III de Madrid. Also, this event actually closes the week of celebrations of the 50th anniversary of this, the creation of this faculty as a separated entity. Okay, so let me just actually thank the other co-organizers which are in the audience, Professor José Ignacio Burgos from ICEMAT, and José Conde from the Universidad Autónoma, and Julio de Vicente, Professor Julio de Vicente from Carlos III. So also I would like to express my gratitude to the Dean of the Faculty, which unfortunately is not here today, Professor Antonio Brespuro, the Vice Dean, Professor Francisco Javier Soria, and generally speaking, all the team of the faculty, the Dean faculty, for their invaluable help in the realization of this event. So, these colloquia are intended to offer to outstanding mathematicians coming to Madrid the opportunity to deliver a seminar in order to discuss an important research topic which could be of interest to a wide community of mathematicians. And Professor Mulase, indeed, is a renowned mathematician, internationally known for his contributions in algebraic geometry and mathematical physics. He was born in Japan and earned a doctorate in mathematics from the Kyoto University in 1985. Then he has been member of many important mathematical institutions, like the Institute of Advanced Studies in Princeton in the years 88-89, also the Institut des Hautes Études Scientifiques Biot-Riemann in 2013, not to mention the many visits to the Max Planck Institute for Mathematics in Bonn. He is currently a distinguished professor of complex algebraic geometry and analysis at the Department of Mathematics, University of California, Davis. And his research lies, I would say, at the intersection of many different areas of mathematics, like algebraic geometry or moduli spaces or Riemann surfaces and X bundles, nonlinear integrable systems, and Gromov-Witten theory, topological recursion, in particular the Einhard-Orantin theory. And among his most remarkable research achievements, let me also mention some of them. A solution to the Schottky problem of characterizing Jacobian varieties, which has been done in terms of the equation of the KP hierarchy. Also, he established a correspondence between the famous Grothendieck's descendant fund and Strebel differentials. And also, Professor Mulase likes to solve complicated conjectures. For instance, the Bouchard-Maligno conjecture on Gromov-Witten, on Hurwitz numbers, sorry, and recently a conjecture by Davide Gaiotto concerning opers of Bellinson and Drinfeld. So the talk of today, indeed, is miraculous integer sequences, and is going to to put together beautifully, I would say, things like integer sequences, the Gromov-Witten theory, spatial values of the Riemann zeta function, algebraic geometry, and even partial differential in ordinary differential equations, actually, in particular equations of the Schrödinger type. So, thank you very much. It's time to leave the floor to Professor Mulase. So, thank you very much for coming. Please, at any time you wish.
Thank you so much for the introduction, and then thank you for giving me this opportunity. Also, this is a wonderful experience to be here back again since the Congress I was here. So I have to thank the Dean, Professor Felipe Ortega, and also the organizers of this opportunity. And then let me congratulate for the UCM for the 50th anniversary of this unification of these 5 faculties, and then also having this opportunity for all mathematicians to get together. So this week we have seen very interesting announcement coming from Stockholm that the Nobel Prize committees anointed artificial intelligence. And then, of course, when you have a finite number of elements to form a molecule, or a finite number of amino acids to form a protein, then yes, it is a finite process to understand how the protein molecule, huge one, can take the shape in 3 dimensions and then do certain activities. So it's a finite process. And then, therefore, it makes sense to build strong computers and then a strong software to predict what happens. But then here, we mathematicians are doing different thing. This is not what the artificial intelligence can ever achieve. And then from even probability theory, we learn that there is a law of large numbers. And then analysis reach beautiful, exact formulas. Using that, you analyze large things, namely approximate large finite behavior from the infinity. But you have to reach the infinity first, not by a computer. And then therefore, I believe this is important and a wonderful opportunity that you have created. All mathematicians come together and then go to the infinity. So let me start from here, but then let me just write down the goal here, what I'd like to talk about indeed in the end. So this is a number, a new friend of mine whom I'd like to know a lot more, but unfortunately I don't. So I'm going to write a positive integer sequence, okay? Which looks like this: -1 to the power n, n factorial to the power squared, summation L plus m is equal to n. And then now I don't have the space, so I have to write it here. 2L plus m factorial m plus 2L factorial divided by L factorial to the 5th, m factorial to the 5th, and then times, times here. So maybe I just write times here. 1 plus m minus, so sorry, L, and then, yeah, I'll define this number immediately. 2L plus m plus 2 times 2L plus 2M minus 5HM. So, well, of course, it doesn't make any sense to write this number for you, right? And why this guy is a new friend of mine, I'll mention it in a minute. Here, HM is what is called a harmonic number. So you just, and then for the convention, I just say H0 is equal to 0. So I said that I'm going to write a positive integer sequence. And then you don't believe it. Why the heck I have to have 1 to the negative 1 to the power n? And then these harmonic numbers are all rational numbers. And then this is positive integer sequence. And then what the heck is it doing? So that's a goal. And then this one has a huge magical thing relating to this theme. But then, unfortunately, he's or she's, I don't know. It is such a difficult quantity. We need some guidelines. And the guidelines, I'd like to explain what I want to achieve out of this number, or maybe a bunch of us we're working on here. So let me start with the Catalan number. This is actually giving us a guideline to attack this problem. So Catalan number is defined to be, say, in many different ways. But just let me just use something appearing over there. So n plus 1 factorial times n factorial. And then even this definition doesn't tell you why this is an integer, not so clear. But then it is a number of many different things you count, always, not always, many times you reach this number. So it's an integer. Then now, what we would like to weave the miracles that this number hides, we use following two differential equations, which I already wrote in the conference talk earlier this week. But let me just try and then explain what kind of miraculous power does this number have, and then go over there to show you what it is doing. So here, I'd like to say, start with a differential equation first. So x squared minus 4, apply this one, x ddx minus 1. And then this one gives you a solution, z of x. And then this equation, if you stare, and if you are a differential equation specialist, you can immediately solve it. It's a very simple equation. Answer is z of x is equal to x plus minus square root. So coming from here, x squared minus 4 over 2. That's a solution you can easily check. Actually, immediately you see that the x is a solution. Differentiate by x and multiply x gives you x and then cancel it. So x is a solution, which is coming here. And then the square root of x squared minus 4 is also a solution, is easy to understand. Then now, if you choose the minus 1 part, then you have a very simple equation. You analytically continue to infinity. Then the zx gives you an analytic solution at the infinity, which is summation m runs from 0 to infinity. This Catalan number comes in, and then x to the power negative 2m plus 1. So this is a solution, which is exactly the same solution with the minus sign, just analytic continuation. So this equation knows Catalan numbers. Of course, in here, you do. So when you plug this in here, you receive the recursion formula over m plus 1 times c m minus 1. And then, of course, you have to choose the initial condition. So that solves the equation. So that is good. But then, so we know this type of differential equation coming from here. That is good. The second one, we don't know very much. So here, I'd like to use a procedure called Weyl quantization. Hermann Weyl. Oh, by the way, quantum field theory and the quantum mechanics are part of mathematics, right? Thank you. There is a nodding from physics professor of Texas Austin, so it is good. So I can do that in math Coloquia. So var quantization here, what you want to do is a variable z, you change it to, so negative sign is because of the just a particular choice, h bar ddx, and then the x, you don't change. So this is a var quantization. And here, I saw this differential equation, but most of you, if you're a student, you recognize this formula. It looks like a quadratic formula. So z and x actually satisfies z squared minus xz plus 1 is equal to 0. So even though I made the differential equation, there's an algebraic equation behind the scene. And then that is not happening here. So that's an extra difficulty over there. So I'm going to var quantize this equation. Then you can immediately see the answer. Answer is h bar squared ddx squared plus h bar x dx. And then because of this equation I'm quantizing, it is now plus 1. And then, of course, since this looks like a Schrödinger equation, I'd like to make unknown function to be psi. One thing comes here is that because you have a 0 at the top degree, this equation has what is called the regular singularity. Therefore, if you solve it as an analytic solution at x equal to 0, it would hit the boundary. And then that is appearing here. So this is not analytic at x equal to plus or minus 2. But at this one, it doesn't happen. Solution has to be entire function. No singularity whatsoever. And then I'm considering x to be complex number. Now you read Riemann. He didn't write much, but his lecture notes are available. He said, the most important property of a function is contained in its essential singularity. That's why we call it essential. So the solution has an essential singularity, and then you want to expand it at infinity. That's what we are interested, okay? Then the solution, psi x. Oh, by the way, maybe going before that, h bar equal to 1, then you can immediately see there's a almost uninteresting solution. This function, which you need to use for grading the exams, this normal distribution function is a solution to this equation when h bar is equal to 1. But don't worry, I'm not grading you. I'm changing h bar to, say, arbitrary number. So this one, I don't know if I have enough space. So this one's solution you can just write. So this is written in the paper Professor Olivier Dumitrescu and I wrote a few years ago. But then the result I'm going to list in a minute. So this one is equal to the following. It's an infinite sum with two parameters. G runs from 0 to infinity, n runs from 1 to infinity, and then h bar to the power 2g minus 2 plus n divided by n factorial. Now I have to erase everything here. May I use everything to erase, or this particular thing is for the screen maybe? Yeah, close. Okay, thank you. So now I don't need all these. Only thing I need is this equation. So where am I? Summation mu is an integer vector of size n. And then I have to introduce a combinatorial number, which I'm going to define in a minute. And then x to the power mu1 plus dot, 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 mu n. So this complicated expression indeed gives you one of the expression of the solutions at the infinity in general, h bar. And then this is indeed associated with some quantum feature. And then so here, I'd like to say a few words about gn, and then mu1 So for the sake of time saving, let me say it without writing everything. So this is actually a number of graphs on a surface of genus G. And then you can see that this is quantized already over there. So let me just give you a definition very quickly. And then with n vertices. And then there are a few conditions I need to say. So one condition is that so you have a graph here. So I don't know, I'm writing here. The graph has to give you a cell decomposition on the surface. And then when you count something, always you have a problem. Suppose you have two objects, they are isomorphic, then you count one. Suppose you have one object who has automorphism of that two. How do you count? 1, 2, or half? So here, I don't want to solve that question, and then I am introducing some kind of mechanism to kill the automorphism. So at each vertex, I choose one of the edges incident, and then cut it. So, label it so that you don't indeed rotate. So the simplest example, G equal to 1, and then N equal to, sorry, Z equal to 0, N equal to 1. You have a sphere. So this is a sphere, not a circle. Sphere, and only one vertex. And then what are the, say, edges like this? And then I need to label one of the, say, incident edges like this so that I cannot rotate it. Now, so the question is, can you just count? Now, so this mu1 up to mu(n) are just the degree of the vertices. So this has to be 2m because any edge going out has to come back, right? So 2m. And then you realize that this picture, you can change into the following. Whenever you see the arrow, I open the parenthesis, and then it goes back, so I close the parenthesis. Open, open, close, close, open, close. And then you notice you have counted how many pair of parentheses are there. Immediately, this is equal to the Catalan number coming out, which means after quantization, the solution still keeps the information of Catalan number before quantizing. So it is a generalization, right? And then there are far more information. Now, this one is slightly degenerate situation. We call in combinatorics a new function in variable in n variables in T to be equal to summation mu as a vector, the same thing I'm writing, and then CGN mu vector divided by mu1 mu n, and then the product runs from 1 to n, xi to the minus mu I. So I defined a new function. And then you have to complain. I said that this is a function in T, and then I didn't write T. What's wrong with it? Well, you remember I just erased here the quadratic formula, z squared minus xz plus 1 equal to 0. And then you just give this in your final exam. The students say, so you say, solve this equation. And the students say, oh, it's easy. X is equal to z plus 1 over z. Do you give a point or not? Well, this is indeed a solution. You didn't say solve it to the z, solve it to x, right? So yes, I'm doing that. So xi is equal to actually zi plus 1 over zi. And then zi I consider to be the coordinate on the Riemann sphere. So zi is equal to ti plus 1 over ti minus 1. So I make this a double complicated change of variable. The last one is easy. It's a Möbius transformation. You plug it in here. You have a horrible function, don't you? Right? Theorem. So I should list all the names, but so many names I have to write because of the number of papers I've been publishing several years ago. So let me just say the names. My former students, Kevin Chapman, Adam Solkin, Michael Penkaba, Brad Safnuk, and then a prominent physicist from Poland, Piotr Sukowski, and then prominent mathematician, Olivia Dumitrescu. So those are the people who have been working on and then established the following theorem. Number one, FGN T is, maybe I just write, is actually equal to the same function if you take a reciprocal of all of them, is a Laurent polynomial. Of degree 6g minus 6 plus 3n. So Laurent polynomial means that it is a polynomial in t variables as well as polynomial in 1 over ti variables. Okay, so it has only finite number of variables. Here, it's a huge sequence, infinite sequence, and then degrees I'm allowing to go to infinity. Yet after this change, it becomes a Laurent polynomial. Okay, Laurent polynomial, then can you just, so in this case, evaluating with respect to x is difficult. But the Laurent polynomial you can immediately evaluate. How about evaluate? So ti goes to 1 over ti, nothing changes. So if ti is equal to 1 over ti, which means ti is equal to plus or minus 1, why don't I choose 1, right? The answer is the following number. So let me write. Oh, my goodness. Do I remember this number? Yes. You should never forget the name of your friend. This is minus 2g minus 3 plus n factorial over 2g minus 2 factorial times Riemann zeta function 1 minus 2g. So I didn't define. So Riemann zeta function is, of course, summation n runs from 1 to infinity, 1 over n to the power s. And then I'm evaluating it at a negative odd number. So this is actually a rational number. And then if genus equal to 0, it has a pole. But the gamma function also has a pole. They cancel. So it's a finite number for all values of g non-negative and runs from 1 to infinity. This is a rational number. But then why the heck are you interested in the Riemann zeta function? This has indeed a topological information. 1 to the negative 1, something like this. It's an Euler characteristic of the moduli space of all Riemann surfaces of genus G with n points. You draw something like this, but it is a space of all complex structures. Then you can define its Euler characteristic. That is encoded in here. So, whoops, interesting note. Then, so that was a surprise that when we are doing that, I was very pleased in some sense. But then it goes beyond. One step beyond, which is, since it's a polynomial, you can restrict to the highest degree part. Highest degree part, T1 up to Tn. So it has to be a 6g minus 6 plus 3n homogeneous polynomial. And then can you write it down? Answer is yes, you can do this. So this is equal to negative 1 to the power n. Yeah, always negative 1 to the power n appears when you change it into the polynomial. I'm sorry, topological quantity, 2g minus 2 plus n. Now I have to do a different partition. d1 plus dn has to be equal to 3g minus 3 plus n. And then this is a notation introduced by Edward Witten. So this has a quantum field theoretic meaning. And then product I runs from n, 1 to n, 2di minus 1, double factorial. Yeah, maybe I don't divide anything. times ti over 2 to the power 2di plus 1. So honestly compute, since the d is changing this way, the degree has to be equal to 6g minus 6 plus n. And then why Edward Witten introduced this number? So I don't explain too much. I'm sorry that I cannot give you all the definitions, but you can just look up any AI-based math textbook tells you this. So this is an integration of the compactified moduli space. So this is not compactified moduli. It is a moduli of all smooth Riemann surfaces. You have to introduce some singular ones. And then the first Chern class of line bundle D1, and then first Chern class of line bundle Dn. And then so quickly defining what I'm doing is that, yes? So I'm restricted to the highest degree terms of this Laurent polynomial. So it's a homogeneous polynomial now, highest, yes. Oh, sorry, I am not writing clearly. So here you have a moduli space bar, and then so object here, a point is a complex Riemann surface, but with sort of nodal singularity possibly. And then you have bunch of points attached. So I pick up the point, say, ith point here, look at the cotangent bundle. So let me call it C. So this is a line. You assign T, P, I, so cotangent line of the curve, and then glue them, and you change the complex structure, everything. You construct a line bundle, Li. And then, so first Chern class I'm taking, which means that since you have a line bundle, if you're a physicist, you use U1 gauge theory, introduce connection, compute its curvature. If topologist, then there's a topological invariant associated with line bundle. So you assign this, multiply them together with power, integrate. That is what this number is. So Witten was interested in this number, and then he made a conjecture that the particular generating function of this number satisfies the KdV equation solved by Kontsevich. When Kontsevich solved, he introduced this function. So accidentally, we recovered Kontsevich's function from this way. Then what can you do? So Kontsevich's solution, and then Witten's idea was that these numbers, if you assemble in the right way, satisfy some recursive relations. He called this recursive relation the Virasoro constraint condition. And then by analyzing our way, you can immediately say, where does this relationship come from? That is changing the graph I wrote. When you want to enumerate a graph, the easiest is you shrink the edge, change it to another graph. What happens, you analyze, write it down in terms of these functions. That is indeed this recursion formula Witten was conjecturing. So all these difficult things coming out can be all translated into the combinatorics here, and then you can explain out of this function. So this is what we found. So this is a 3. And then this gives us a prototype that we wish to understand or apply to this number. Okay. Now, so let me just, so these are the things I have done in the past, and then I'm talking about what I'm trying to do in the next probably 25 years, possibly, if I can finish. So, as I mentioned, we are the ones to reach the infinity. there's a very counterintuitive theorem. So this is the first part. It's all done. The next one. So there's a theorem here. Let me say in a few words and then write a statement. Suppose you have a real number. Suppose you have a rational number, sequence of rational numbers, approaching or approximating this real number. Okay? But if this approximation is too quick, then counterintuitively, the limit has to be irrational. So that is what the counterintuitive, in a sense that probably AI has hard time understanding it, because you have a good rational number converging to this unknown number very quickly. It's got to be rational, isn't it? Right? So the theorem. Let R be a real number. Suppose there are infinitely many O-prime pairs P and Q. And I just assume Q to be positive, that doesn't matter. So that, so there's an infinitely many, right? So absolute value of R minus P over Q. So P over Q is approximating this given number, right? But then rapidly converging, meaning that I want this to be smaller than Q to the power 1 plus epsilon, where epsilon is a constant. So for any P and Q, epsilon is a fixed constant, so that this happens, right? So this is what I mean, that you have a rational sequence approximating R, but I don't allow it to be equal. If it is equal, then it's a rational number. So you don't have to approximate, right? Then R cannot be rational. R is irrational. So this is an extremely simple theorem, and then probably you have learned it in kindergarten, right? So let me just, since I completely forgot everything I learned in kindergarten, let me just give you a proof. So proof. Sorry, I didn't mean to change the color. Suppose R, Y indeed rational number, so A, B, an integer. Then, so let me quick, because I really need more time here. So this condition, R is A over B minus P over Q. And then it should be smaller than this, which I'm going to write. But before that, let me just keep writing. So this difference is easy to compute. It's a B times Q. So here, yeah. And then AQ minus BP. But you're not allowing this to be equal to 0. Numerator has to be at least 1, because these are integers, right? Which means it's, sorry, which direction am I going to write? So larger than 1 over BQ, and then sorry, I wanted to write this is non-zero. But then this one is assumed to be Q to the power 1 plus epsilon, right? And then you can see immediately, therefore, Q1 plus epsilon is smaller than BQ, which means Q to the epsilon is smaller than B. Didn't I say there are infinitely many such pairs? Which should force that the number of Q's to be infinity, and then such Q can be only finite. It's a contradiction. So it's a simple theorem. And in this simple theorem, actually I have never seen this used to show any interesting number to be irrational, except for this guy. So now, so this is the second part and then third part. Sorry, I shouldn't have used this. Oh, is it also usable? Oh, yeah, okay, thank you. Now the third part, I'm going to go to my new friend. and then I want to do something. So all these things I want to use to understand. So which way do I want to? Let me think. Yes. So why don't I just reveal the nature of this equation? So this number, so it's a third part, it's a second part, plus 51n squared plus 27n plus 5 sorry, this one is plus 1 un plus n cubed un minus 1 is equal to 0. So this is the recursion. I wrote a recursion for Catalan that was very simple. This is a recursion for characterizing this an. Now this recursion is three-term recursion. And the space of solutions is two-dimensional. And the an is one of them. I'd like to choose another relatively simple solution. So another sequence, another solution of this recursion, Bn, I'd like to define by B. So in this case, of course, I didn't say that. Can you calculate A0? A0, to make n equal to 0, L and M are all 0. So this is 1, this is 1, this is 1, 1, 1, 1, and then all these are 0. So from here, you can calculate A0 is equal to 1. And then if you are good enough in the morning, you have the 10 cups of double espresso, you can immediately calculate not A5, A1, and then do the same thing, you get the 5. And then a little more coffee, A2 is equal to 73, A3 is equal to 1445, and the A5 I completely forgot. So you can do that. Yeah, they are all integers. But that is miraculous in many ways. There's no reason to believe. But they satisfy this recursion. Then you realize, if you know the lower numbers, top one, you are multiplying by huge number. So it's very hard to believe that the integer would give you a solution. This is a very rare solution. So I choose B0 to be 0. Isn't it simple? Then B1 can be chosen anything, but you choose a particular one. B1 equal to 6, sorry. And then in this case, B2 is already not an integer. And then you generate the entire sequence. Then, so I didn't say too much about analysis. Now I'm going to go to analysis. Because these days the difficulty of math colloquium is that math is compartmentalized, and then it's very difficult for an analyst to understand in such a stupid integer theorem why this is important. And then number theorists never appreciate the importance of analysis. That's bad. So let's do everything, right? Analysis. I'd like to calculate the following integral. 0, 1, 0, 1, 0, 1, and then dx, dy, dz, oh my goodness, x minus z plus xyz. So I have to be honest, I don't know exactly how to calculate it. So I just punched into Mathematica. Mathematica thought about a while. I thought that the Mathematica would give you an approximate answer. Mathematica immediately say, not immediately, for a while, it is equal to zeta of 3. Riemann zeta. And so I checked how smart Mathematica is. I asked the following. 0, 1, 0, 1, 0, 1. Now it's much longer. Sorry, isn't it fun to do all this stupid integration? X, y, z, 1 minus x, 1 minus y, 1 minus z. And then x minus z plus x. So you see, this is not symmetric, right? That's the whole point. To the power n dx dy dz over x minus z plus xyz. Oh, this one mathematically used a considerable amount of time, and of course, mathematically didn't understand n. So I have to do n equal to 0, 1, 2, 3. Then, for a moment, answer came out. Okay? A sub n times zeta 3 minus b sub n. What? A n is this. B n is defined this way. So yes, you can redefine a n from this sequence. Answer is this. Okay. Another final exam question. Suppose you have two integers a, b, not integers, I'm sorry, real number between 0 and 1. Then a plus b over ab, of course it should be positive, but that's smaller than 1, right? It's obvious. You can just immediately prove it. Now, you see the region of integration is between 0 and 1. You have two numbers, say x and xyz. You're adding together, multiplying together here. So the entire thing inside is less than 1. So you can immediately see, take n goes to infinity limit. Where does it go? This guy goes to 0, right? Because the absolute value, it's a positive number anyway. X minus, well, it's a bit, you need to be careful. But the absolute value goes to 0. So this goes to 0, which means limit n goes to infinity, bn over an has to be zeta 3. So that integral knows about zeta 3. Now let me prove zeta 3 is irrational by the theorem I proved, okay? So how you do that? Yeah, anyway, whatever I remember, I can reproduce all the times I can relate this, sorry. Now, so there's a fact. So this is, again, difficult to prove using the formula and then the induction. You can prove that the dn cube multiply bn is indeed a non-negative integer, where dn is the least common multiple of 1, 2, up to n. So this fact is known. And then computer simulation tells you, yes, we do use computers a lot. The denominator of bn is well approximated by the, sorry, did I say what? No, it is the least common multiple. CLM, no. Least common multiple, sorry. So what is the least common multiple? So least common multiple time, yeah, sorry, 1 to n. So this is by definition the following. It is all prime less than or equal to n, and then p to the power. So you have to choose the largest power appearing among the numbers. So log n over log p, and then take a floor. So this is the definition of least common multiple. But then this is at least same prime p. If you remove floor, you get larger, right? But then p is equal to e to the log p, right? So log p cancels. So this is equal to p e to the log n. What? E to the log n is equal to just n itself, right? Because, yes, you understand that, right? Okay. Yeah, because e is, well, but then what is it? This is n to the number of pi. Number of pi's between 2 and n. And then number of pi using this zeta function I'm erasing, you can approximate that it is n to the power log, n over log n. Sorry, am I using this wrong, right? Did I do it wrong? So p e to the p log n, and then was it correct? Yes, and then n is again e to the power log cancels. So this is equal to e to the n. Sorry, that is a conclusion. So dn, which is an integer, is well approximated as e to the power n. Okay? So using these facts, you can indeed approximate. So yeah, for the importance of the time, let me say the following. So what you are trying to do is zeta 3 minus bn over an. And then you need the two following estimation. Sorry, I just erased. So this incredibly, I just erased it. So let me just write again. So these integers are really important role playing. So from this equation, you have the estimation un is, when n is large, approximately c to the power plus minus n, where c, you can read it here. So you just approximate the un plus 1 is a c to the power n plus 1, c to the power n, c to the power n minus 1. You solve it, you get the quadratic equation. So c is indeed 17 plus 12 square root of 2, because so 17 is a half of that. And then I'm writing a square root of probably 18 times 16 by quadratic formula. So this is so un behaves either exponentially fast growing or exponentially fast decaying. So we know this goes to 0, means that this one is exponentially fast decaying. An is exponentially fast growing. This is actually approximate c to the power 2n, 1 over c to the power 2n. Now, for the sake of time, let me just suppress the proof. Using this fact and the theorem, you can cook up the nice formula. What is epsilon? You can define. Prove zeta 3 is irrational. So Bn is not integer, but the ratio is a rational number. You can approximate the denominator by all this analysis. And then a key fact E. E is what? Is less than C. That was a key fact you need to show this is irrational. Okay, so let me come down to this number. So this number is used by Roger Apperi to show that the zeta 3 is irrational. But he didn't use this expression. This expression came from the paper, long paper by the following people: Tom Coates, Alessio Cotti, and then Golkin, and then Kasprzak. So these 4 people wrote a huge paper in Gromov-Witten theory of Fano threefold. It's one of the Fano threefold whose genus 0, 1 marked point Gromov-Witten invariants was written in that paper. Not exactly this, but then using this way, all right? So let me just reveal all these miracles that this number tells you. So let me define two generating functions. This is summation n runs from 0 to infinity an t to the power n. And then alpha t is just, so now it is famous, well, subject in algebraic geometry, which is resurgent theory. So I'm using a Borel-Laplace transform, and then so I define these two, okay? So if you know an, you can calculate these functions. Now, Gromov-Witten invariant of genus 0, 1, so like a Catalan situation of T for the particular Fano, I'm not going to, I have to probably define quickly, but a manifold is, this is actually equal to exponential minus 5t times alpha t. So geometry tells you a sub n. So it's a Gromov-Witten invariance calculated from here. And this generating function at satisfies a Picard-Fuchs equation. In particular, so here, why don't you, so again, for the sake of time, let me just do this following. Summation n runs from 0 to infinity of gigantic thing, putting t to the n. Then this is summation n runs from 0 to infinity t to the n, right? Now you can compute this. It's a what is called a geometric series, right? So you can immediately calculate. So this is equal to half, and then so it's a 1 and 0. You just calculate everything, and then there's another thing here. So it is actually very simple. X minus z plus xyz plus t times xyz, 1 minus x, 1 minus y, 1 minus z, and then dx, dy, dz, because I use this once again. So there's a t here. I'm sorry. Oh, if I did make this mistake, you should subtract point. I'm using geometric series. So this is the answer. And then several years ago, Boykers and Peters, the German mathematicians in Netherlands, and working in that region, realized that this denominator is equation for the K3 surfaces. And then this K3 surface is associated with so the manifold X. So this is a Gromov-Witten of the manifold X. So X is actually realized inside the Grassmannian of 2, 5. So this is Grassmannian of parameterizing planes in 5 space, which is embedded in projective space of 9 dimension. And here you need 3 polynomial equations to cut it off. And then this X has a natural divisor. Name doesn't matter, but it is called anti-canonical divisor. So X is 3 dimension. This is 6 dimension. This is 9 dimension. So the divisor, which is a codimension 1 subspace, this is a K3 surface. That is defined by this formula in the affine part. So indeed, this knows which manifold are you talking about, for which you are talking about Gromov-Witten theory. And then I don't have the time. They do satisfy differential equations of 2 types. One is Picard-Fuchs. One is more or less having only one essential singularity at infinity. 0 is also a solution. And then these are related by what is called Borel-Laplace transform. One is analyzed by these numbers. The other one, my guess, which I haven't proved yet, unfortunately, you expand at infinity, that should contain higher genus Gromov-Witten invariants of this variety. But that is a sort of easy conjecture you can make, and a lot of people believe. Professor Tempesta was talking about topological recursion I've been involved in. So many people believe that that kind of thing should exist, and then there must be some kind of curve. Catalan case, it was a quadratic curve. this case, it's not easy to find a curve, but there must be a curve whose Weyl transformation is equal to the complicated differential equation. Sorry, I didn't write, but that has to be that. And if using that, analysis can tell you Gromov-Witten invariance of all genera out of this. So sorry for the overtime, but let me just close it here. Thank you so much.
Does the interpretation as a Gromov-Witten invariant give you? Does the interpretation as a Gromov-Witten invariant give you some insight into the recursion relation satisfied by the ANs, which was mysterious to me when you wrote it down?
I don't know the answer, but for the Catalan situation, it was a Witten's conjecture. And then, yes, we were able to understand by the combinatorial way your question. Should the Gromov-Witten invariant satisfy like a Virasoro constraint coming from there? I believe that should be the hint so that we should interpret that way to get the higher genus thing, which we do not know yet. But that is exactly the reason I wanted to point. Catalan case is this. Why don't you hope for and then find it? Thank you for great question.
Thank you very much for these very nice mathematics. So I just curious to know whether this could be also adapted to get other values of the Riemann zeta function, say for 5.
So thank you so much for the great question. Indeed, there are many mathematicians and then even some physicists working in the last few years. Can you really bring it to zeta 5? Or at least from the geometry, there's a sequence of Fano 3-fold. You can easily write down the same way. Don't you see a lot of structures? Answer is yes, in the sense that the structures exist. They call them Aperi-type Fano 3-fold, Aperi-type theories. Nothing leads to your crucial question at this moment. So that seems to be different. So why do we know that all even and the 3, shouldn't we go to 5? So unfortunately, the answer is not known at this moment.
Other questions or comments? So thank you. I was thinking about your construction. So if I understand correctly, you start from Catalan numbers, and so you generalize them, and you get a sort of mirror-symmetric equivalent, right, of the
Yes.
Catalan numbers via discrete Laplace transform. Right?
Yes, exactly.
Okay. So I remember a long time ago that Professor Boris Dubrovin used to say that mirror symmetry is a sort of a kind of Laplace transform.
Yes, it is.
So this goes somehow in this direction, right?
Yes.
And then after, so starting from this Laplace transform, you construct a partition function for which solves your Schrödinger equation. Yes. So how much of this construction is somehow specific, and how much could be generalized in some sense? So starting not from Catalan numbers, for instance, from some other integer sequences having a combinatorial meaning. So is it possible to somehow to think to something like that?
Yes, so the question is that how much can you just have more a general theory out of this Catalan story? And then there are many rational number sequences, like what they're called Hurwitz numbers. For them, yes, you have the similar situation. And then Gromov-Witten invariants of not Fano type, but Calabian type, in particular toric Calabian. The University of Columbia mathematician, Melissa Liu, and then her students developed the same way to generate all the Gromov-Witten invariants from the 0-1 kind of thing. So there are some examples. But then the relationship with this interesting number theoretic things, which are more like a Fano situation, and not the Calabi-Yau symmetry, which is sort of, we shouldn't say easy, but structure-wise similar things. You can get something. It is very different things we are trying to do. Their answer is very slim. So hopefully this one would be a good answer, but we don't have the insight yet.
Some other questions? Yes, a question. So we have this particular recursion, and the possible solutions is just two-dimensional. And we see that if I look at one solution divided by the other solution, this approach is a set of three. And in fact, if I choose any two possible solutions, the quotient will approach some rational combination of set of three. In the sense that any other rational solution will be alpha an plus beta bn, and then my impression is that the quotient will approximate. So the only transcendental number that appears will be set of three, and all the others will be rational combination of set of three. On the other hand, if we look at the asymptotic behavior, you say that the two solutions should be one solution that approximates to, that behaves like c to the n, and the other behaves like c to the minus n. So the quotient will be like c to the square, which is an algebraic number, not the limit. What will be the limit of, I mean, in some sense, we have this c, which is algebraic. The question is how a number that we expect not only to be rational, but to be transcendental, appear in such an algebraic equation. So what is the link? Because theta 3, we expect it to be transcendental, not algebraic, not just irrational.
So the question is a great question. One was able to empirically prove that zeta 3 is irrational. Does this hint anything about algebraicity or not, right?
Yeah.
And then one motivation of developing a bunch of us doing is that, as I said, there are differential equations. And then that has this particular function as a solution, at zeta 3 minus bt, right? Mm-hmm. And then it has a differential equation called OPAS in the community that Professor Laurent is working on. And then the question is that there's a conjecture. If the equation is defined over Q bar, algebraic numbers, or on the manifold defined over Q bar, all the monodromies are all in Q bar, then such equation should come from geometry. Mm-hmm. Now, so this situation, we don't really know exactly all these equations we are writing has a geometric origin, yes, but is zeta 3 can be put into the monodromy data. Now, algebraic geometers don't believe that the zeta 3 being, for example, algebraic can be proved in such a stupid thing. But then this is just a conjecture, and then converse does not have to be true. Mm-hmm. But then, yes, there is an interesting way of thinking. This algebraicity and then difficulty of Hodge conjecture is behind the scene. So that's another reason why people are interested in this kind of question. So yes, it's a great question. It's a monodromy question. Yes, and which I didn't have time to explain today. But thank you for the question. Oh.
The formula that you wrote down there on the left down corner looks like you're calculating periods for the Calabi-Yau given by the complement of x minus the divisor. But then you were saying that Gromov-Witten is Gromov-Witten of x, so it shouldn't be Gromov-Witten of the mirror-Landau-Ginzburg model, or?
So yes, it is exactly the period, and then I'm talking about the mirror-Landau-Ginzburg model, and then yes, this K3. So what you have to write is that indeed I'm writing the family of K3 surfaces, and then I'm writing the period integral, and then as a function over t, writing down the Gauss-Mann connection, and then that is a differential equation satisfied by at zeta 3 minus bt. Yes, so that's Landau-Ginzburg, and then period integral is appearing over there, which is mirror to this Fano threefold. Yes. Well, of course, this mirror is not a standard way of seeing it, right? One can interpret it that way.